Hello, everyone, and thank you so much for joining us today. We're very glad to see such a strong turnout for this topic because it's one that comes up in almost every operation that we talk to. Today's session is called Why Failures Feel Sudden and What Top Operators Do Differently. I'm Alicia O'Brien, and I am the VP of Marketing here at MSAI. What we're really going to explore is why so many failures seem to come out of nowhere, even when in reality, they don't. But before we get into it, just a couple of quick housekeeping items. We're going to keep the session to about 45 minutes long. We'll leave time at the end for Q&A, and feel free to drop questions into the chat as we go because we're going to be monitoring them throughout. And this session is being recorded, so we'll share that afterwards as well. Now, let me quickly introduce the speakers that you're going to be hearing from today. Firstly, we have James Newman, who leads product management here at MSAI. He focuses on how we translate reliability strategy into customer real-world solutions, helping teams detect issues earlier, prevent failures, and drive better operational outcomes. He brings a strong background across product strategy and industrial operations and spends a lot of time working directly with our customers on how to improve their performance at scale. Also joining us here is Luke Grice-Lowe, sorry, Luke, our Director of Reliability and Maintenance Programs. He brings really deep hands-on reliability background, including building and scaling the global condition monitoring and predictive maintenance program at Amazon. He spent years working directly with critical assets, teams, and systems, figuring out how to actually detect failures early, not just analyze them after the fact. So between the two of them here, we've got both the strategic and the practical sides of this topic covered. But before we dive in, a quick bit of context on who we are here at MSAI. At a very high level, we focus on condition-based monitoring and early threat detection, helping teams move from reactive response to early proactive visibility. What that really means in practice is we're collecting and analyzing multiple sensor data streams, thermal, visual, and others, and bringing them into a single platform to give those teams real-time insight. The goal is simple, not just to tell you when something is wrong, but to help you see when something is starting to go wrong. So these organizations that we are working with, uptime is absolutely critical across logistics, energy, infrastructure, manufacturing, data centers. All of these logistical operations have a common thread. When something fails unexpectedly, the impact is significant, which is exactly why early threat detection and closing these visibility gaps is so important. Which brings us to the idea of continuous visibility. With MSAI Connect, the focus is on detecting degradation before alarms trigger, before you're already in the failure event. That could be things like subtle temperature changes, imbalance patterns, or localized anomalies, signals that typically show up well before a traditional alarm would fire. So instead of reacting to failures, you're identifying those trends and changes early enough to actually do something about it. And that's really the foundation for today's discussion, because the reality is most failures don't happen instantly. They feel sudden because we didn't have visibility early enough. So on that note, I'm going to jump over to James to take over from here. James, presentation is now in your hands.
Uh, Thank you, Alicia, and thanks to all of you for joining us today. As Alicia said, we want to start with a simple idea today that might sound just a bit counterintuitive, and that's the most sudden failures aren't actually sudden. They may feel sudden, but reality, that's usually a perception problem and not a physics problem. Failures don't really surprise us because they happen instantly. They surprise us because we weren't looking at the right place at the right time and in the right way. So, Luke, as we start our conversation today, let's kind of start with a very simple question. Why do organizations still describe failures as unexpected?
Yeah, so it's a great question. Where I think when people say unexpected, what they really mean is we didn't see it coming. And that usually comes down to two things: visibility and targeting. Most organizations have effective processes in place for analyzing failure after it happens. We've got root cause analysis tools such as Five Whys, Fishbone, fault trees, FMEAs. But what we don't often do is redesign detection before the failure. So we end up in this cycle where we understand what went wrong, but we don't change how early we can see it next time. And in my experience, 9 times out of 10, it comes back to something quite simple. The frequency and method of detection doesn't match how quickly that failure develops.
So, so in our modern world, one would kind of expect that this is going away, but in fact, it sort of seems to be getting harder. We would think that with more technologies and more data streams, this would be getting better. But in reality, is it?
And that's the interesting part. We've got more automation, more assets, tighter margins, less tolerance for downtime than ever before. So it's not that reliability and maintenance principles have changed or it's getting harder. It's that the level of precision required has gone up significantly. So we need to be more effective within these constraints. You can't rely on general playbooks anymore. We must be more targeted and deliberate with our strategies and move away from this one size fits all. And then the other shift is, reliability is a program or one technology or owned by an individual. When in reality, reliability is a culture within your business. It's a cross-functional team of diverse skill sets and backgrounds. You've got operations, engineering, maintenance, and even HR. They all have to align around that same outcome.
Right, right. HR always cracks me up when you say that because how many HR people think about that, right? But really, that combination is the backdrop for our conversation today because as our environments are becoming more automated, as they're becoming more electrified, as they're becoming more uptime dependent, the window to detect these kind of problems is actually getting smaller, not larger. So let's go just a bit deeper into that and get a bit more technical. Tell us a little bit about what's actually happening along the failure curve.
I think the simplest way to think about it is assets behave a lot like people. As we get older, we start to feel small signs, little pains, little changes, nothing catastrophic, but signals that something isn't quite right. The same is true for mechanical electrical assets. They degrade over time. The challenge is those early signals do exist, but they're either not being measured or they're just not being interpreted properly. Now, yes, there are some failures that happen very quickly, but most of what we deal with in operations are not instant failures, that they're missed signals.
So if that's the case, why do operators today still tend to only see problems at the very end of the curve?
A lot of it comes down to human limitations. We act on what we can see, hear, or feel. And when you think about condition monitoring technologies, they're really just extensions of those senses. Thermography is vision, ultrasound is hearing, vibration is touch. And it's the reason why sensory checks are still considered within the P2F curve, just very late within that curve. But even then, we're after applying those tools in a way that doesn't target the failure mode. So we're still detecting problems. We're just not early enough to change the outcome.
Interesting. So almost every organization that we've either been part of or that we work with, they have some sort of inspection and alarm system, and obviously on paper they should help. So what's missing?
They should, but only if they're deployed properly. So the mistake we see a lot is assuming that we're having tools equals having a strategy, when in reality it doesn't. Programs degrade over time if they're not actively managed. We can look at the second law of thermodynamics, entropy. If you don't put energy in, it tends towards chaos and disorder. However, the real issue tends to be, wrong technology, wrong frequency, targeting the wrong failure mode. So you end up measuring something, but not the thing that actually fails. You consider this measuring the effect and not the cause.
Excellent. So let's make that just a bit more concrete. Where are you seeing today traditional monitoring approaches breaking down the most?
All the
And,
time.
and yeah, maybe say one more thing. Maybe the second question to answer there is how often do issues develop shortly after an inspection? It's the other half of the question.
Again, all the time.
Yeah.
because scheduled inspections are just that snapshot in time. You capture a condition at a moment, but degradation is happening continuously. Yeah, I ran a study when I was at Amazon looking into this. We wanted to understand whether our inspection frequency was effective on our critical assets. And what we found was pretty eye-opening. We missed around 20,000 events in a year, just in the gaps between those inspections. So the conclusion was simple. The inspection frequency didn't match the failure rate. And when we looked at fixing it, we couldn't just, 4x the labor decrease that inspection frequency. It just wasn't viable. So what you're left with is a structural visibility gap or finding a continuous monitoring solution.
Good. So, okay, so now alarms and signals, lots of those and our HMIs and other places today. What's missing there?
Yeah, so this is another big one. Alarms are typically designed to protect the asset, not to detect early degradation. So by the time you get an alert, you've got overcurrent, something's already inefficient, thermal trip, something's already damaged. And control systems like SCADA, tend to show you the effect, not the cause. So you see a fault, but you still have to figure out why it happened. But by the time the system tells you something wrong, you're already in the event.
Right. So I would summarize by saying what we know about traditional monitoring, it tells you when something is wrong, but it doesn't give you enough visibility into knowing when it's starting to go wrong. So let's make this a bit real. So let's imagine a high throughput logistics operation. It's automated, it's tightly coupled, it's very dependent on a few critical assets. What actually happens in that environment?
So typically what you'll see is degradation starting very subtly. It might be a slight increase in temperature, a small change in vibration, nothing that would trigger an alarm. But then you layer in like non-engineering variables such as environmental changes, throughput changes, load changes, stop-start cycles, and then that degradation accelerates. So now if you're relying on monthly inspections, you've got no visibility into that trend. The signal emerges and evolves in between that inspection cycle. So when you finally see it, you're already close to failure. You have lost that visibility of your dynamic environment.
Yeah. So what changes now as we add in this concept of continuous visibility?
Everything, everything. Instead of seeing, a point in time, you see a trend. You can correlate signals, thermal increase, vibration change, electrical behavior, and now you're not just detecting a problem, you're diagnosing it before you even step onto the floor or you're walking up to that asset. Instead of like unexpected stop, on the spot diagnosis, downtime impact, you move to planned intervention, predefined diagnosis, controlled maintenance windows. The failure didn't start the day it stopped. The visibility just came too late.
Right. And I sort of gave a sneak peek by accident, but let's take a chance and take a look at what it looks like for a user. Let's take a moment here. Let's walk through a couple of use cases that show us how this addition of continuous monitoring helps uncover the blind spots in operations. So walk us through a couple of examples from a user perspective.
Yeah, so one of the pros that we can actually see here is uh, how visual it is. So straight away, it's visually striking. If you see the image on the right, it's very much stable. The image on the left, you can see that clear impact area or that thermal load. If you were, let's compare it. So if you were to do a scheduled routine inspection now, visual, and you went and looked at that piece of equipment, the likelihood of you seeing that is next to none. So that asset that's actually broke there is a knife end roller, and that's within the belt. So unless you were doing an uh, intrusive maintenance and actually strip down that component, you'd never see the failure. You'd never see it. However, what you do see with that constant trending, you can see that spike, and then with coupled with that thermal visual live monitoring, you can actually see where the progression starts. You can start seeing where the source comes from, which gets you closer to the diagnosis point, and then eventually the team can replace that failed component.
Yeah, it's interesting there because what it also does is the same image that shows you the problem now shows you it's fixed. So now you have the continuous feedback loop, right, of repairs, which is a
Yeah,
superpower too.
that it's a brilliant one because it's one thing that a lot of people forget to utilize when they do fix monitoring or condition monitoring. I like to use the term confirming the fix. So, has that work or remedy that we've done paid dividends? Do we
Yeah,
have the benefit to show for it?
excellent. All right, let's talk about some more.
Another one, dynamic environment. So this is a loose load. Basically, if you were to walk past that conveyor right now and it's constantly moving, the environment's very dynamic. Throughput isn't exactly um, predictable. So what's actually happened here is a piece of amnesty got stuck in the end, which then caused the belt to track. And obviously, when you look at belt tracking, you have a very finite amount of time to respond because eventually that belt's going to track long enough for it to cause delamination on the side of the belt, snag in, rip it, boom, gone. You need a new belt. So live monitoring systems, and especially when they're integrated to, webhook alerts, work order management, and on systems, however that alerting is, it's all about getting the person there and making them alert as soon as possible, especially when you look at these quick SLA failures.
Right. Right. And the nice thing about this particular one is that you can see it both in the data and visually, right? And so someone could take action and fix it. No SLA loss, no operational loss. Work continues. Great. Let's take a look at one more. A little bit different.
I think personally, this is probably one of the most underrated analysis methods of condition monitoring. So there is a lot of power and stature given to things like, your machine learning, your ISO standards, and all them, the good, proven methods, but comparative analysis, especially when you look at hyperscalers in logistics, e-commerce, where it is very much rinse and repeat standard model build outs, you have a lot of the same equipment. This is a perfect example within a live electrical cabinet. You got two fuses running under the exact same load. Um, One of them is close to 150 degrees hotter than the other, which shouldn't be happening. And actually, as you can see from the comparative analysis that's done across the two with the reference and the actual, um, it's night and day. You don't need vast skill training to understand that there's a problem at this point. So when you kind of look at, there's a term where you can consider low low skill, high will. This is very much a low skill, high will. We want people that are interested in it. You can teach skill all day long. Skill comes with time as you interpret data, as you see the visuals. And as you can see the results of that, where we started seeing insulation breakdown on the wiring, the fuse housing started to melt away. Wouldn't have got that. And if you consider NFPA 70B is a 6 month inspection frequency, when was the next time you were going to look at that without live monitoring?
Yeah, and I think this one too, even if they did, in the routine inspection, as you said, right, this is a closed panel. You're probably not opening that up. It's also a case that when the system's powered down, you don't see this, right? You wouldn't see this power down. There's no, unless you looked at the insulation and saw the degradation, you would never see this in a normal maintenance window because everything would be shut down. It would be no different temperature difference. So it's a really powerful continuous monitoring to do that.
There's a real interesting point as well when we look at electrical monitoring and cabinets is that safety and that high risk operation. Opening up them cabinets is a high risk anyway. So if we can reduce the interactions that our teams and have with these high risk operations by inserting a piece of technology that can do it for you without even having to open the door and makes you aware of the risk before that door even opens, it's a bonus in my book.
Yeah, it's just, and it's sort of the real win, right? That when we have these continuous monitoring visibility, catching these early signals, improving safety, they all change the way we do maintenance. They change our maintenance practice. And things move from unexpected and perhaps dangerous to anticipated and planned for. And really that's all we all want to be, right? So let's think a little bit about now about implementation. So what is it that top operators do differently that others could take advantage of?
I think so. When you look at teams that do this well, it's not about the tools, it's about behaviors. So, continuous versus snapshot thinking. They focus on change over time because in a fast moving environment, a snapshot it's not going to be enough. There's too many dynamic variables. Uh, Multi-signal thinking is probably another good one. They don't ask what's wrong. They ask what combination of signals tells the story. For example, SCADA shows a current increase. Vibration confirms it's mechanical. Thermal shows me where it is. Now you started to diagnose that issue before you've even got to the asset. Most importantly, and I can't stress this enough, it's the big one for me. If you're trying to do these programs without a foundation layer, you're off to a non-starter. So lead with a criticality strategy. You know, they're very deliberate about where they're going to invest. Not every asset needs the same level of monitoring. It comes down to severity, frequency, detectability, contingency. Good operators don't monitor everything. They monitor what matters properly. So what all of this really does is change the type of event you experience. You move from that emergency to planned, reactive to proactive, and downtime to continuity. And that's the key shift. They don't eliminate failures. They change how they show up in the operation.
Awesome. So Luke, thanks so much for that. Lots of very powerful insight there. Appreciate you sharing that. It's very tactical, what it looks like in the field. My hope is and my belief is that we probably call some people to start thinking about their own operations and their own practices, and it was exactly our goal. And um, what we wanted to do, a couple final clean takeaways here. What do we hope you get out of today's session? And really, it's a few things. First of all, as we said at the beginning, and we've said a bunch of times today, we don't really believe that most failures are sudden. The issue is that you just didn't detect the right signals at the right time. The degradation was there, visibility wasn't. So we can fix that. The traditional monitoring often just sees the state of a point in time, but it often doesn't give you the visibility you need into degradation. And most of the risk we see today isn't really about a lack of data. It's from visibility gaps to having the right data in the right way to monitor the right thing. And lastly, teams that are getting ahead of this are being very deliberate about both how they invest, what they detect, and where they position themselves on the failure curve. So what we hope you've gotten today is a clear visibility and some thoughts to help you think about the way you're running your own program and how you can maybe do that a bit differently and how continuous coverage can begin to help you accelerate your journey towards anticipation as opposed to unexpected failure. Great. So thank you all for joining us today. We appreciate that. We do have a few questions coming in. We're going to take them. If you haven't put them in the Q&A yet, please go ahead and do that. As Alicia said at the beginning, we'll be trying to watch that and we'll monitor that. If we don't get to your question today, we will in fact try to get you back an answer so you're not missed. Let's start off with a question, Luke, for this question here. It comes from Mark. What's the most common failure mode you see that organizations are constantly missing with this with early, right?
Uh, to be honest, I think the ones that you miss are the ones that you haven't got visibility of. And I tend to always come back to those electrical failures. It tripped or we lost power, that type of stuff. And it's more reporting on the effect, not the cause. So why did it trip? The bearing of fail caused overcurrent, which then thermal cut out, everything tripped. I think electrical's probably the most unseen.
Good, thanks for that. All right, Sarah has a question. It says, so how do you decide where to invest in monitoring versus accepting risk?
I don't think I can stress this enough. If you are not starting with a criticality assessment, you are throwing money at a wall and hoping some of it sticks. Criticality will help you define what you need to do, how you need to do it, and what you can invest. If you do your criticality correctly, it will define a return of investment for you.
Interesting. Return on investment, the holy grail for every one of these programs, right? To prove it has
Yeah,
value. Good. So question from Amir. If a team wanted to improve their detection capabilities tomorrow, where should they start?
they should probably start by giving me a call. However, in reality, without going back to the fundamentals of criticality, what you should do is a gap analysis. Understand where your gaps are. So if you take what you're currently doing, right, I'm doing these inspections, I'm doing this PM frequency, I've done a PM optimization and all that good stuff. However, I'm still getting failures in between. So have we understood our failure modes? You know, do we get the right inspection frequency in place? Do I need to increase my detection frequency? It's the best place to start. If you look at the amount of failures that you have between that start frequency to the next one, then you're not meeting the failure mode. It's also worth considering your mean time between failure as well. If you've got a really great mean time between failure and you're spending loads of money keeping it there, does it still need a criticality assessment, as an example, should be a living document. It shouldn't just be something that you do once a year and throw away, because the more you get in control and the more detection methods you bring into something, that criticality can shift because we've got more control. The mean time to repair is better. The mean time between failures increased. So it's always worth bearing that in mind as well.
Excellent. And so Katie has a question. Says, do you think most organizations actually understand where they sit on the failure curve?
I don't think you sit on a failure curve as an organization. I think you sit on, a technology. You can understand what you're trying to detect and how you do it. I think sitting on a failure curve in terms of an organization probably isn't the right approach if that's how you're scoring yourself. What we want to do when you look at that failure curve is almost define it to what your failure mode is. So we always consider the failure curve as this nice, clean downward curve with your ultrasound, your vibration, your oil analysis, your thermography, your sensory, your functional, all that good stuff. However, depending on the failure mode, that completely changes. You take an electrical failure mode, all of a sudden, oil analysis isn't in there, vibration isn't in there. You haven't really got a sensory check you can do on it. So you're left with two, where we're looking at ultrasound airborne or we're looking at thermography. So it's about tailoring it to what you want. So when you look at that, design installation, point at which a failure can be detected, the functional failure, there's that level above it where it's about criticality assessment, understanding the failure mode you're trying to target, and be deliberate with that method you're trying to bring out.
And then, of course, obviously bringing multi-sensor AI into the picture to help you do all of that, right? Of course, yeah, yeah,
You know where to find me.
yeah, yeah, exactly. So one more question, and this one's from me. So, Luke, if there was one mindset shift that you wanted people to take away from today, what would it be?
I think I'd say this is a personal gripe, but not go that far. It's the amount of people that go, "Oh, we've got a reliability programs team," or "We've just done vibrations, so we're okay on our reliability." You know, in reliability as a program or a technology or an individual person or even a team isn't the right mindset. If you're trying to do reliability correctly, reliability is a massive, criteria and curriculum. So just defining individual things as reliability, it needs to stop because it's not the right mindset. Reliability is a culture. It's not one thing, one person, one technology. It's that vast, diverse, different perspectives, all driving towards a common business goal. So I think if we can leave with anything, remember reliability is a culture. And if the culture doesn't fit, you cannot achieve reliability.
Yeah, amazing, amazing. So, Luke, thank you very much. Again, thank you to everyone in the audience for joining us. Alicia, back to you.
Excellent. Thank you so much to the two of you. The main takeaway here, I think, is pretty simple. Failures aren't actually sudden. They really feel sudden because we just don't have visibility early enough. So we appreciate all of your time. And if you'd like to see more or learn more, see actually MSAI Connect in action, you can visit our website at www.multisensorai.com and request a demo or to speak to an engineer or a reliability expert. We'd be happy to walk you through it. We'll be sending out the materials pretty quickly after this session. Otherwise, thank you, James. Thank you, Luke, and have a great rest of your day.
Thanks all.